Hello and welcome back to another validation example for the Autodesk Inventor Nastran program. I know it's been a little bit of a while if you uh, are a follower of the channel. Been kind of busy, been meaning to get back to it, and found myself with some time today. It's a holiday in the US and thought it would be a good use of time, so hopefully you enjoy this one. Um, as far as the example is concerned, this is going to be a pretty simple one to set up and analyze. It is a buckling of a straight bar with the lower end fixed and the upper end free. So it's going to be a straight bar. Again, just as described, the lower end will be fixed, the upper end will be free. It will be a bar that's 10 inches long, made of steel, and will be 0.5 inches in diameter. We will apply a 10-pound downward load and determine when the bar becomes elastically unstable. It's a pretty simple example. You could use the hand calculation to validate it. What you should find is that the buckling load multiplier would be 227.1, and that would equate to a load of 2,270.97 pounds force. Uh, I do want to go over it though for two reasons. One, we are going to be using a beam element or bar element within the Inventor Nastran program. We don't get to use those very often, or I should say, a lot of us tend to live with the world of solid models, right? We have a lot of CAD models that either we create or the designers create, and then we're analyzing those. So it's nice to see how to be able to work with beam elements whenever we have the opportunity. They're a nice simple element to work with. They analyze really fastly. And then the second part of it is when you do get into a more complicated model, the buckling analysis to do it by hand becomes much more complicated. So it's good to be a little bit familiar with this analysis type. So let's go ahead and get into it. Let me move the Excel sheet out of the way. If you've watched some other videos, you know, once we get our results, we'll come back and plug them into the spreadsheet here and see what the percent difference would be. So let's go ahead and start with our model. I'm working out of Inventor Professional 2023 here. I could be a little bit more precise on that. It is 2023.2. I believe there's a .2.1 out right now. If you're not working with the latest Inventor, that's okay. What we're going to use here within the Inventor program, the Nastran program, are functions or features that have been in the software for a long time. So even if, say, you're using like a 2018 version or even 2017, you should be able to replicate the same steps. So how do we create this geometry? It's nice and simple. I'm just going to start a sketch. And in this sketch, what we want to do is go to the, well, I'm going to work off the XY plane. And for beam elements or bar elements, line elements, we should say, for analysis, we just need to create a sketch. So I'm going to create a line, and I'm going to start that line at the origin. Remember, it was a 10-inch long vertical line, so I'm just going to go up a little bit, left click again. I'll hit escape to drop that line, and then we'll dimension it, and we're going to make that 10 inches long. Press enter. So there is our vertical line that will become our beam element. So nice and simple, easy to construct. And then we're going to say finish sketch. Now, before I leave the Inventor environment and go over to the Nastran program, dimensions will follow through into Nastran, and it could be helpful for you. For me, I just find them to kind of be in the way. So I'm going to come over, right click on sketch 1, and I'm going to turn off the dimension visibility. So at this point, now we can go into the Inventor Nastran program. Notice that the bar changes a little bit so that I can use my FEA tools, and we're ready to go ahead and set it up. So if you have watched some of the ones with solid models, you know that as you bring a solid model into the Nastran environment, it automatically sets up an idealization, right? And the idealization is what holds the information about what the element type is, what sort of material it is. Since we just brought in a sketch line, at this point the program doesn't have any idea what we're going to do with this line. So we do need to create an idealization. So we'll just select the idealization command. We're going to change it from being a solid element type to a line element. And then below that, I'm going to choose the line element type to be a beam. Either one, the bar or the beam, they'd both work for this example. The beam just has a little bit more capability to it in some situations. Again, this one, it wouldn't matter whether you choose a bar or a beam. And then to define what that section is, there's a cross-section input here. So I'm going to go ahead and click on cross-section, and then we'll click the icon just to the right of that. And here we have a number of different cross sections that we can choose from. We're going to choose a rod, and the diameter in our case is 0.5. It's looking for dimension 1. You can see the diameter is defined here as 2 times dimension 1. So what it's actually asking for is the radius input. So our radius would be 0.25. And I like to do a draw A end. That then shows me what the section is, and it also calculates the properties. So if I wanted to do a quick validation of the properties, I could do that if I had, say, a textbook here, or if I wanted to quickly calculate what the area was. We'll just go ahead and say OK to that. And again, I'm going to say OK. So that defines the element type and what that section looks like in this case. Underneath the idealization, if I expand the plus sign under beam 1, that's where I get to my material. And here I have the material properties that we're going to input. For the density, pretty common steel properties, we're going to type in 0.000 7324. For my modulus of elasticity, 30E6 or 3E7. And then Poisson's ratio will be 0.3. So I can just type them in. Technically, yes, there is a library here. You could go into select material, bring this over onto this monitor, and I could scroll down and I could select, from the libraries that are here. But pretty simple just to type in those properties, except that I just wiped them out. 30A6 and 0.3. There we go. Okay. All right. Not a whole lot more we have to do to it. We do need to change the analysis type. This is a linear buckling analysis, so I'm going to double click on the analysis type, bring that over to the proper monitor. That is a linear buckling analysis we're going to do, and say OK. So we need our constraint, we need our load, and our mesh. So in mesh settings, as far as the problem description, suggests an element size of 1 inch. So we're just going to go ahead and type in the element size of 1 inch. That will give us, 10 elements along the length of it. We don't need it to be a parabolic element. We're just going to use a linear element. And we'll say OK. So when we do that, you can see the elements. So hopefully you can see that on the video. Transitions from a light to a dark color, whatever color was associated with that idealization. So there we can see our various elements. There's a lot of detail that you can get out of beam elements when you are post-processing the results. So you might want to know, a result at the A end or the B end of the element. So that's why we give the shading to it. So kind of neither here nor there for this particular example. If you did want to check the cross-section, you can right-click over on elements. You can see here we have 11 nodes, 10 elements. You can right-click here, and you could always say, well, you can display the orientation of it. It's a round cross-section, so that's also kind of very relevant. More important whenever you have a section with different properties with different axes. But we could also display the cross-section so we could see what that section looks like. We can see that we have a round section there. Okay, so let's go ahead with the setup. We're going to do some constraints. I'm going to select the base of this, and we're going to say that we want to make that fixed. So translations and rotations are all already set. And then our load is a 10-pound force. I'm just following the example here. I'd say -10, so that we can match up with the book answers typically. So we're not saying that this particular force is going to cause this to buckle. That's what this solution does. This solution says, okay, you have this particular amount of load on it, so I'm going to give you a factor, and that factor times the load that you have assigned to the model. That's what will initiate the buckling. So I don't expect that 10 pounds force here is going to cause it to buckle. But if it gives us a factor of 2, that means 2 times or 20 pounds force would cause it to buckle. Or if it gives us a factor of 10 times the 10 or 100 pounds force would cause it to buckle. So typically what I do when I'm running these analyses when I can, I'll just type in a magnitude of 1 here in this field. So then whatever the multiplier is that comes back, whatever the factor is that comes back, that is equal to, multiplying the one load input, the 1 pound force that I put in. If it comes back with a factor of 5,236, 5,236 times the 1 is then my buckling load. So it's just simple math. So I typically just use a 1 here and let the factor equal what the multiplier will be. But anyway, just for consistency's sake with the problem setup, we'll use 10 pounds force. Still an easy thing to figure out. We'll say OK. And at that point, I think we are ready to run the analysis. This should be a super quick run here. And there we go. So what we get out of this analysis, there we can see mode 1 and the eigenvalue of 226.8. So again, what that's saying is 226.8 times the 10 pounds force is what would initiate buckling for our structure for this simple model. So you can see what we got theoretically was the 227.1, or at least what the book came up with. So if I type in 226.82, we are 0.12% different than the book, so nice and close there. And then again, our if we multiply that by 10, so it would be 226.8. Whoops, 2268.22. That would be the buckling load, how many pounds force the program is predicting, the particular analysis is predicting, and there I get 0.12% different than what the hand calculation tells us it should be. So very nice agreement between the book and what we can do within the software. Hopefully that's a nice, simple, quick example. It's a good analysis to run, which I think often gets overlooked, particularly when you have long, slender structures. You're going to do a linear static analysis on it and ensure the displacements might not be bad, the stresses might not be very high, but it could still be susceptible to buckling. So particularly if you're doing, again, long, slender structures, it's a pretty quick analysis type to run, and hopefully this example helps you get into that type of analysis. So thanks for watching. Take care. Have a great day.